In this lecture, we will continue with our discussion of the various properties of the Fourier transform. To start with, let us consider aspects related to energy. Suppose f of t be a voltage signal. Now, let us imagine that such a voltage is given to a 1 ohm resistor. Then, if f of t is a periodic signal, then the power dissipated in this 1 ohm resistor is from minus t upon 2 to plus t upon 2 of f square t dt, the average value 1 over t naught. This is called the power dissipated in the signal, or we often refer to as power available from f of t, power available from f of t. So, irrespective whether the signal is a voltage signal or something else, normally we refer to this as power available from f of t. Of course, this will be quite appropriate if f of t is a voltage signal. Even otherwise, we can refer to this as a power available from the f of t. And this is a periodic signal, and we saw that this quantity, the power available from the signal, can also be obtained from the Fourier coefficients as n from minus infinity to plus infinity of C n magnitude square. This is a relation which we have already discussed when we talked about the Fourier series expansion of a periodic signal. Now, what we would like to see is how this concept can be extended in the case of a f of t which is not periodic. F of t is aperiodic, and we also assume that it has got a finite amount of energy in that, in the sense that minus infinity to plus infinity of f of t magnitude dt is finite. So, this is a restriction which we already imposed on finding the Fourier transforms of the various signals that we have considered so far, and we also assume that this is also true. So, if this is so, then when you divide by t naught, when t naught goes to infinity, then the power becomes 0. So, when we talk about aperiodic signals of this type, where the square of the integral is over the infinite band of frequencies, infinite time is finite, then there is no meaning in talking about power, because power becomes 0. So, all that we can do in such cases is only calculate the value of this integral f square t dt, and that has the dimensions of energy, because we are not dividing by t naught. So, this is energy in the signal is finite, is non-zero, energy available from the signal. So, when we talk about aperiodic signals, it would be more convenient for us to talk in terms of energy available from the signal. Therefore, we will have this particular heading for this topic, energy considerations. So, in the case of aperiodic signals, we talk about energy available from the signal, where we talk about periodic signals, we talk about power available from the signal. So, we would like to see what is the energy available for the signal in terms of the Fourier transform. So, the energy that is dissipated in this 1 ohm resistor is given by this. So, that energy in 1 ohm resistor energy dissipated in the resistor is minus infinity to plus infinity of f square t dt, and this I would like to write as minus infinity to plus infinity, t running from minus infinity to plus infinity, f of t, and for the other f of t I use the inverse Fourier transform formula, which is 1 over 2 pi omega from minus infinity to plus infinity f of j omega e to the power of j omega t d omega. This is the expression for the f of t. So, instead of writing f square t, I multiplied f of t by the another equivalent expression for f of t times dt. So, this has got two integrals, one on time domain and one in the frequency domain. What I would like to do is interchange the order of integration. That means, instead of integrating in the omega domain first and then later on the time domain, I would like to reverse the roles. I would like to integrate this expression in terms of time domain first and then in frequency domain later. So, if I do that, then I want to integrate in the frequency domain at the second stage. So, I will put this outside, and all terms involving omega and which do not involve time can be brought outside. Therefore, f of 1 over 2 pi will come out, of course, f of j omega will come, and the rest of the terms are f of t e to the power of j omega t, and of course, d omega will also be outside, and you have dt f t e to the power of j omega t. These are the terms that are left. So, in the time integration from t minus infinity to plus infinity, I have f of t e to the power of j omega t dt. Now, let us look at this. If it had been f of t e to the power of minus j omega t dt, it would have been straight away f of j omega. But instead of minus j omega t, we have plus j omega t. Therefore, this whole expression now becomes f of minus j omega. So, this can be written as 1 over 2 pi omega from minus infinity to plus infinity f of j omega d omega, and this quantity is f of minus j omega. And as we already observed that for real functions of time, where f of t is a real function of time, f of minus j omega is the conjugate of f of j omega. Therefore, this will become 1 over 2 pi omega from minus infinity to plus infinity of f of j omega magnitude squared d omega. So, the power available, the energy available from the signal is given in time domain in this fashion, in frequency domain in this fashion. Now, f of j omega squared magnitude squared can be thought of as energy density. What it means is, around a band around omega, if we consider a small band of frequencies delta f, f j omega squared times delta f is the energy concentrated in that band centered around omega. So, this energy density is expressed in terms of joules per hertz per cycle per second. So, in a small band of frequencies centered around omega, this will be f j omega squared magnitude squared df, which is delta omega by 2 pi, is the energy available energy in a band delta omega centered around omega. So, if you take a small band of frequencies centered around omega, small delta omega, this is the energy that is available. All we have to do is, therefore, to find the total energy, you have to sum up all such energy say quanta in different bands, and that becomes this integral, that becomes 1 over 2 pi minus infinity to plus infinity of f of j omega magnitude squared d omega. So, this is an interesting relation that f of t, this of course is minus infinity to plus infinity of f square t dt. So, you can calculate the energy in time domain as minus infinity to plus infinity f square t dt, that is the energy, that is called the energy available from a signal f of t. You can also calculate the energy available from the signal in frequency domain in this fashion. F j omega squared is energy density, energy available for cycle per second. So, you have to multiply by frequency d omega by 2 pi, and integrate over the whole range of frequencies, you get the total energy that is available from the signal. These relations, relation is for the periodic case and this relation for the aperiodic case are usually referred to as Parseval's relations. It is also occasionally referred to as Plancherol's theorem, particularly in the case of the aperiodic case. So, the Parseval relation in the case of a periodic signal is in terms of the Fourier coefficients. In the case of an aperiodic signal is in terms of an integral involving the energy density f of j omega magnitude squared t omega. To summarize the discussion here, when you talk about an aperiodic signal with a finite amount of energy, then you can't talk about the power available from the signal, which is going to be 0, because the base is T naught is going to be infinity, the average power over the complete time period is 0. We can talk about only energy, and the total energy available from the signal can be computed in two ways, one in time domain in this fashion and one in the frequency domain. The meaning of this is, if this is a voltage signal and this is given to a 1 ohm resistor, this is the energy that is dissipated in that 1 ohm resistor. You can calculate it in the time domain or frequency domain as the case may be. Now, let us work out an example to illustrate this particular concept.